Hi everyone, in this video we are going to discuss on tutorial 12. The topic is angular displacement and angular velocity. We are going to divide into three parts. This is part 1. So we read the question. The radius of the earth is 6,400 kilometer and it takes 24 hours to make a complete rotation and about its axis. So what is the angular velocity of the earth rotation about this axis in radian per second? Then question B, what is the speed of a person standing on the equator as the earth rotates? Okay, so we are given radius of the earth, then the time taken to complete a rotation here. This means a period, and we are going to find angular velocity. Okay, for question A, we can see from here that we can use angular velocity here equals to 2 pi f, and f is 1 per t. So we substitute all the values into the equation here and we get 7.27 times 10 to the power of negative 3 radian per second. Okay, so the hours here we convert to second. So 24 hours times 60 times 60. Okay, next question B. What is the speed of a person standing on the equator as the earth rotates? So we are going to find V. So we can use the relationship V and angular velocity that we found in A. Okay, so you can imagine like in the animation given here. Okay, so a person standing on the equator. Okay, so V equals to R omega. Omega is angular velocity. So we substitute the radius, okay, convert to meter. And then the angular velocity from A into the equation here. And we get the speed 465 meter per second. Okay, so that's answer for question 1. Okay, we go to question 2. A stone at the end of a string of length 1.50 meter is whirled in a horizontal circle on a smooth surface. So the speed of the stone is 0.80 meter per second. So what is the angular velocity of the stone? And then how many revolutions does the stone make in 1 minute? Okay, so you can imagine like this as the diagram show here. The stone attached at the end of the string. Okay, and it is whirled in a horizontal circle on a smooth surface. Okay, so the given in the information given is the length, which is equals to the radius of the circular motion, and the speed of the stone. Okay, so for angular velocity, we can use the relationship between V and angular velocity, which is V equals to R omega. Omega is angular velocity. So angular velocity equals to V over R. So we substitute the speed and then the length. So we get 0.53 radian per second. Okay, next question B. How many revolutions does the stone make in 1 minute? So this is revolution per second. So this 1 minute is not period. It's not period. So the questions means one's frequency, yes, because this is revolution, the number of revolution per minute. Okay, in 1 minute here means the unit for frequency is RPM. So we find F first. So to find F, we can use the angular velocity from A, which is equals to the 2 pi F. So F is angular velocity over 2 pi. Okay, so we calculated already the angular velocity from A. We substitute into the here, and we get 0.084 revolution per second. So this is angular velocity in the unit revolution per second. So we can find, but the question is 1 per minute. So we can convert this second per minute. So to convert in minute, we multiply it by 60 because 1 minute is 60 seconds. So we get 5.1 revolution per minute. Okay, in RPM as the questions wants in the unit RPM. Okay, so if in the exam you forgot whether to multiply it by 60 or divide it by 60, so you can use ratio method here. So for 0.53 over 2 pi, this one means angular velocity for 1 second. RPS means in 1 second. This is the what we calculate just now here. So if in 60 second, 1 minute is 60 second. So how many frequency? Okay, so we can use ratio here. That means we need to cross multiply. Okay, so next we go to question 3. So that's the end of part 1. So we go to the next is part 2. Hi. So this is the part 2 tutorial 12. The subtopic is centripetal acceleration. Okay, in question 1, the figure shows a particle in circular motion. So mark the direction of the velocity v and the centripetal acceleration a when the particle is at the point A and point B. So on the diagram here, we mark the direction of v, which is tangent to the point A. Okay, the velocity direction is tangent to point A, and at B, the velocity is tangent to B. Okay, the velocity is constant. Okay, at all point. The speed is constant at all point. So direction of A is towards the center of the circle. So we direct the arrow here towards the center of the circle. Okay, now we go to question 2. A particle is in uniform circular motion. So use Newton's laws of motion to explain why the particle accelerates, and then explain why, although the particle accelerates, its speed remains constant. Okay, so to use Newton's laws of motion to explain why the particle accelerates, so you need to know the acceleration, the definition of acceleration. So the definition of acceleration is the rate of change of velocity per unit time. Okay, next, why there is a change of velocity? So you need to know what is the meaning of change of velocity. So in the change of velocity is direction in the velocity. Okay, so that's why there is a change in velocity. So you write down direction of velocity changes in circular motion. So you can see from the animation here. So the direction always change. Every time it moves from one point to another point along the circular motion. Okay, next step, we are going to use the Newton's laws of motion. So the Newton's law, we can use Newton's first law. So we state, according to Newton's first law, there is a resultant force on the particle. Okay, so because the direction change, so that means there is a force act on the object. Okay, so then mentioned in the question also loss. So there is a S there, loss. So that means more than 1 Newton's law. Okay, so we use the Newton's second law. So according to Newton's second law, the particle accelerates in the direction of the resultant force. So this is from F equals to ma in the Newton's second law. So when there is a resultant force F, so there is also a acceleration. Okay? So now we complete what the questions wants to explain why the particle accelerates. So all here are the points on to answer question A. So now we go to question B. Explain why, although the particle accelerates, its speed remains constant. So because the direction of the acceleration is always perpendicular to the velocity. So you can see here the acceleration is always perpendicular to the velocity. So we discuss on in terms of diagram why acceleration is perpendicular to velocity. Okay, so this velocity acceleration is downward towards the center of the circle. Okay, so imagine the object move from A to B. So velocity at A is VA and velocity of B is VB. So VA is equals to VB. So VA, we use vector diagram. So VA this way, VB is this way. So the change in velocity will be in this direction. So VB minus VA. So we use vector diagram. And then the angular displacement is theta. Okay, so this form a vector diagram, label the theta here. Okay, now acceleration means a change in velocity over time, rate of change of velocity. So you can see that A equals to VB minus VA over T. So from the vector diagram here, the A follow the direction of VB minus VA. So A direction is this way. So VB minus VA in the vector diagram is also this way. Okay, so for a small angular displacement, okay, this theta, for a small angular displacement, we find that the VB minus VA here is approaching in the situation where it's perpendicular to VA, VA, and VB is the same, so it must remain the same length. So at VB VB goes nearer to VA, so you can see that the arrow here is pointing perpendicular to VA, or in other words, perpendicular to both actually VA, VB, because VA is equals to VB. Okay, so that's mean A direction is perpendicular to the V. Okay. Okay, so that's end of part 2. Next, we go to part 3. And in tutorial 12, part 3, we are going to discuss on topic centripetal force. Okay, question 1. In a performance, a motorcyclist is just able to go round a vertical circular track of radius 6 meter. So the total mass of the motorcyclist and his bike is 180 kilogram. Then calculate the angular velocity of the motorcyclist. So can imagine like this. Okay, the motorcyclist able to go round the vertical circular track. Okay, so we draw the diagram as a circular track here, and then the motorcyclist at the top of the circular track. So the force that act on the motorcyclist is the weight of the motorcyclist together with the bike, and another force is the reaction by the motorcyclist with the wall of the track. Okay, so from the centripetal force is provided by these two forces, R and mg, and R and mg is in the direction of centripetal acceleration. So R and mg is positive. So R plus mg equals to the centripetal force is mv squared over R. So the radius is given 6 meter. We can either use this equation, or another one we can use mr omega squared for the centripetal force. So if we use this one for the motorcyclist able to go round, so it means R equals to 0. Okay, this is the hidden information we can get. Then we substitute into here, we get mg equals to mv squared over R. So cancel the m and we get v equals to square root of gr. So substitute the radius 6 meter and the g is 9.81 into the equation. We get speed 7.67 meter per second. But the questions want angular velocity. So we use v equals to r omega and omega equals to v over r. Omega is angular velocity. So we substitute this into here, divided by the radius 6, and we get angular velocity is 1.28 radian per second. Okay, so if we use this equation, also we can get the same for the cyclist to able to be at the top, manage to go round at the top. So this means R equals to 0. So substitute into here, we get mg equals to mr omega squared. Cancel the m and we get angular velocity equals to square root of g over r. So same as this one, but here we go direct because we substitute at the earlier part already. V here equals to r omega. Okay, so now we substitute g 9.81 and r radius 6 into the equation and we get the same answer, 1.28 radian per second. Okay, so now we go to question 2. A particle is suspended from a point A by an inextensible string of length L. Okay, it is projected from B with a velocity u perpendicular to AB, which is just sufficient for it to reach point C. Okay, so show that if the string is just taut when the particle reaches C, its speed at C is given by V equals to square root of GL. Okay, we are going to prove this. And then question B, use the principle of conservation of energy to show that the speed u with which the particle is projected from B is given by u equals to square root of 5gl. Okay, this u equals to 5gl, square root of 5gl. And then lastly, the question is calculate the tension in the string when the particle is at the lowest point B. Okay, so we go to question A first. We are going to prove speed equals to square root of GL. Okay, so the particle just sufficient to reach point C. So that means the tension in the string is equals to 0. Okay, so at point C here, the force is tension, which is downward, and another force is mg. So these two forces provide the centripetal force. So it's in the direction of the centripetal force. So that means T and mg is positive. So T plus mg equals to, we use mv squared over r because we are going to find V. Okay, so now T equals to 0 because it's just sufficient to reach point C. So T must be 0. So we cancel the M. We get V equals to square root of GL. So it is proven that V equals to square root of GL. Okay, so now we go to next question B. Question B, we are going to use we are going to find u which is equals to square root of 5gl. So we are going to show that also. So the question asks to use principle of conservation of energy. Okay, so that means total of energy at B is equals to total of energy at C. So the total energy at B will be kinetic energy plus potential energy at this point. Okay, so potential energy at point B is 0. So kinetic energy only involved here, and it is equals to half mu squared. Okay, then the total of kinetic energy at C will be potential energy and plus kinetic energy also. So the kinetic energy at C will be half mv squared. We can substitute V into here, and then potential energy at C will be we use mgh. Okay, so the V is from question from previous question B, we get V equals to square root of GL. So we substitute into here. And then the H is the diameter of the circular track, circular motion. So which is 2L, diameter. The length of the string is L. So that means the diameter of the circle is 2L. Okay, now we can solve for U. So cancel all the M. Okay, and then cross multiply by 2 for all the terms. We get u squared here equals to, here is GL because square here. So that means GL. And then here is 2 times 2. We get 4GL. And 4GL plus GL is 5GL. And then the square here becomes square root of 5GL. So it is shown that U equals to square root of 5GL, okay, at point B. Okay, shown. Next, we go to question C. Question C, we are going to find tension at point B. Tension in the string. Okay, so the tension in the string direction is towards the center. And then another force that act on B is the weight of the particle, which is equals to mg. Okay, so centripetal acceleration is upward, so therefore T will be positive. So T minus mg. So the centripetal force is mv squared over r, so it is provided by the T minus mg. mg is negative because it's opposite of the centripetal acceleration direction. Okay, so the v is we can substitute the v here is this u, so we calculated already in b. Okay, so we solve t equals to mu squared over l plus mg. We bring mg to the right side, and then the u is 5gl, okay, in b. And then we cancel the l, we get 5 mg plus mg is 6 mg. So the tension in the string is 6 mg. So this is the answer. Okay, next we go to question 3. A stone at the end of a string is whirled in a horizontal circle above the head. So explain why it is not possible for the string to be in the horizontal plane. So got mistake in typing error here. So FOR only. So B, draw a diagram to show the circular motion of the stone. Okay, so when we whirl a stone, okay, the question, we go back to the question. So explain why it's not possible for the string to be in the horizontal plane. Okay. So the string is whirled in a horizontal circle above the head. Okay, so when we whirl above the head, so it whirls imagine whirls like this. Okay, so the force that act on the object will be upward and downward force. So what is that force? What is that force? And for it to move in a horizontal circle, so we have left and right. Okay, left and right force. So we have upward and downward force, which must be balanced if the object or the stone must be whirled in horizontal circle. Okay, but this is impossible to occur if it is whirled horizontally. Why? Because there is no upward force. Okay, upward force is provided by the vertical component of the tension in the string. So this is the stone attached to the string. So the tension in the string component for upward must be there. Okay, but if it were horizontal, there is no vertical component of the tension. Okay, so we are going to prove this by calculation. And the radius of the circle must less than L, so that this tension component upward of the string we must be there. So the radius of the circular motion must less than the length of the string. Okay, so how to imagine this? So we go to the calculation part. So this is tension in the string, okay, which is towards the center of the circular motion, but the string is inclined at angle theta with the vertical, so that we have the component of t. So the component of t will be t cos theta and then t sin theta. Okay, so this is the component of the string. So the tension in the string is towards the center of the circular motion. So this is the stone. So the another force act on the stone is mg, weight of the stone. Okay, so t cos theta must be balanced by mg to remain the horizontal circular motion. Okay, so at horizontal circular motion, the angle theta is 90 degrees. Okay, 90 degrees. So can imagine like in this diagram. So this is horizontal. This is not horizontal at angle theta. So L equals to R at this position. Okay, and the mg is 90 degrees to the tension in the string. So this is if you imagine we draw in diagram. Okay, so the angle here becomes 90 degrees. Okay, angle with the t become 90 degrees. It's not a theta, this theta angle. So it will be 90 degrees, which is not possible because cos 90 degrees is 0. So that's why it's not possible. By calculation, we can see already here it's not possible. There is no component of tension, okay, to balance the mg. So it's not logic. Okay, not logic because no force to balance the mg. Okay, so therefore to draw the diagram to show the circular motion of the stone is this diagram. Okay, next we go to question 4. A coin is on a turntable that rotates at 25 revolution per minute. The coefficient of static friction between coin and the turntable is 0.30. So explain why the coin stays stationary relative to the turntable if its distance from the center of the turntable is less than a certain value of R. And then find the value of R. Okay, so this is the turntable and the coin. Okay, so it is rotating in this angular velocity, which is given as 25 rpm, revolution per minute. Okay, the mu is 0.30. Okay, coefficient of static friction is 0.30. So we are going to explain why the coin stays stationary relative to the turntable if its distance from the center of the table is less than a certain value of R. So I'm going to use this R to small letter R because this is distance, distance. So to avoid the confuse when using the reaction force later. Okay, so I change the distance into small letter R. Okay, so now this is the coin. Okay, the force that act on the coin will be mg, and then centripetal force is towards the center of the circular motion here. So the upward force will be reaction force by the turntable. So that's why I use small letter for the distance from the center of the turntable, just now R, to avoid the confuse with this reaction force. Okay, so now the centripetal force is provided by the static friction because the coin remains stationary. Okay, stays stationary. So from the centripetal force is provided by the static friction here. Okay, so will be equals to mu r, and the centripetal force we are going to use mr omega squared because angular velocity is given here 25 revolution per minute. Okay, so R is equals to mg. Okay, R is equals to mg because the coin doesn't fly. Okay, so that's mean the R is equals to mg. So it remain its motion in a horizontal circular motion. So R is equals to mg, and we cancel the m and we get we arrange the equation here becomes R equals to mu g over omega squared. Okay, so for stationary, static friction must be less or equals to the limiting static friction. Okay, so limiting, so that's mean R equals to mu g over omega squared. So we can substitute this into here to the coin, for the coin to stay stationary. Okay, so this is the condition for the coin to stay stationary. So that's mean the mu r is larger and less than mr omega squared. Okay, so this is the answer. The radius, the radius, the radius or the distance from the center of the turntable, which is also equals to radius of the circular motion, must be less or equals to the mu g over omega squared. Okay, for the coin to stay stationary. Okay, so if exceed the limiting static friction, so that's mean the coin will start to slide. Okay, next we go to question B to find the value of R, right? The distance from the center. So to find the value of R, so R must be equals to the mu g over omega squared. So we substitute mu is 0.30, so g 9.81 into the equation, and angular velocity is given by frequency 25 rpm. So we convert to 2 pi f, omega equals to 2 pi f, and the minute we convert to second. So 1 minute is 60 seconds, so 25 over 60. Okay, so we get 0.429 meter. So this is the distance should be for the object to stay stationary. Cannot larger than this value. Okay, so that's all for part 3.